Hello everyone. So today we're going to continue on 8.2, which hopefully we'll finish up 8.2 in today's video. So the last thing I actually want to talk to you about 8.2, hopefully will be a short video today because I only have one thing to show you, is to how to calculate what we call surface area of a solid or revolution. So you actually learned something about it last year, where you learned that you can rotate a regions around an axis to form what we call solid or revolution. So in BC calculus, you have learned to find the volume of what we call a solid of revolution. And so if you don't remember, let me show you. So here's, let's say you're given a curve y equal to f of x from, let's say, A to B. And so here's the regions that you want to rotate. And yes, we're going to just talk about what happened when we have a regions where, excuse me, one of the boundary is actually the axis revolution, which in this case I'm going to just rotate around the x-axis for simplicity. Okay. Then this region will form some kind of solid. So the solid would have a circular cross section because it will actually rotate to be something like this. Okay, something like that. So that will form some kind of solid that looks something like this. So how do we actually calculate this volume? Well, we use what we call the dis method. So I'm not going to go through the process of why the way the formula is, but simply just, I guess we'll just briefly talk about it, but I'm not going to try to derive it. And the derivation came from, obviously, from Riemann sum. Okay, so here's how the volume is. The volume will go from integral from A to B, pi f of x squared dx. So in this expression right here, the f of x is basically referred to as the radius of the disc. And so pi f of x squared become the area of the disc, which is pi r squared, technically a circle. But because of this, it has to have a thickness. The thickness is actually defined by dx. The thickness of the disc. So essentially what happened is the process actually goes something like this. If you pick a point and you draw a line. So this is my f of x, which act as the radius. The problem is that this thing is a curve on top. But if we pretend that it's not a curve and have a slight thickness to it, and then this would basically form a rectangle with a width of dx while a height of f of x. And if I take this thing and I rotate it around that will form a nice disc right in the middle of a solid. Now it doesn't actually give the actual volume because you can see that definitely there's a little bit stick out of the curve because I'm pretending that this thing is a rectangle. But if I make this thin enough, it should give me a good estimate. And once I have the estimate, I can improve it by using more discs, which obviously involve the summation to infinity, which is the reason why I turn to an integral. So hopefully you remember all this from basic calculus. And you also might remember washer method, where you actually have some kind of hollow in the area in the middle. But we're not going to deal with that. We're just going to pretend that this thing doesn't have any hollow ground and you form a solid revolution. So what we're going to try to figure out is actually not the volume, because you already know how to do this. What we're going to try to do is the following. What if we want to try to now find, this is the question, is how about we try to figure out how to find what we call the lateral area. That means the area around the solid, not the top, not the bottom, but around, because we know the top and the bottom are both circle, and we know how to find the area of a circle already. So that's not very interesting. We're interested in what we call the lateral surface area. How to find the lateral surface area of a solid or revolution. So, as a matter of fact, the idea is actually very much exactly the same. The only difference is, instead of using this disk and try to find the volume of this disk, what we're going to try to do is simply find the lateral area of this disk. And then the same process happens. I just simply add them all up. So we can definitely go ahead and give it a try to figure this out. Okay? So, to kind of try to make this into something that we can figure it out, I'm going to go ahead and let's define the following. Let's say we're given a curve alpha in R2. We're going to keep it simple, let it R2. Let's say its parameterization is given by the function g of t equal to x of t, y of t, where t go from, let's say, a to b. And let's say, to make things simple, let the axis of revolution be the x-axis. Now let's look at a picture and see how that works. Okay, ready? So the picture actually looks very much the same as the one that we just did. So let's say here's my alpha, which is basically given by x of t, y of t. And let's say here is t equal to a. Notice that define this point to be x of a, y of a. Okay, and let's say we have a second point right here, which is at t equal to b. So that defines the point x of b, y of b. So don't try to label that on the x-axis and say a and b, because that's not the case here. And let's say I form a solid, and I'm trying to find the surface area of this solid. So how do I do that? So, well, what I'm going to do is the exact same thing. What I'm going to do is I'm going to pick a point somewhere in the middle. I'm going to say this is at t sub k. And so we know the position at this point would be x of t sub k, y, comma, y of t sub k. And if I now rotating it, remember the size rotate around the x-axis, here's our axis of revolution, then this line would basically form our radius. And then if I rotate it around, then this thing right here will basically be 2 pi times the radius, 2 pi r. And I can define the thickness to be based on how long it has to go. So therefore I'm going to pretend that the thickness is what we call ds, because that will be like how long the arc length is. Notice some of you might think, well, can it be called dx because you make it horizontal? Yes, but actually no, because that would not be quite long enough to be the actual length between this point and the next point. So I'm going to have to use dx to represent how long it is. Okay, and if you think about it, this is kind of magnified. So let's say you have a curve. Let's say here is one point and here is the second point. dx represents this distance. ds represent this distance, which you can see that in this case ds more clearly represent how wide this strip should be, okay, because it's basically the distance between 2 points. So that's why I'm going to have to call it ds instead. And therefore, if you think about it, then at t sub k, the surface area, which I'm going to call SA, would have to equal to 2 pi r, which is basically how the y value is, which is y of t sub k, multiplied by the length of, well, ds sub k, which is basically, since the r-length differential, length of g prime of t sub k dt. So that gives us the surface area for this one strip. And actually I probably say that's a sub k. So now I can go and find the total area, which I'm going to call S sub a, where approximately is equal to the summation k from 1 to n 2 pi y of t sub k length of g prime of t sub k dt. So that will be a sum of all these little circular lateral area of this add together. But of course, that's just an estimate. So if I want to actually get the actual area, I can say that if I let this process go on forever, that will actually get the actual lateral area of this solid. And yes, once again, what we form is a Riemann sum. And so that Riemann sum is going to converge to a area, which I'm going to go and call, let's form that formula and then I'll give you a definition. So that will become the integral from t sub 0 to t sub 1, 2 pi y of t, the length of g prime of t, which I'm going to write as radical x prime of t square plus y prime of t square dt. Now, if you look at this integral and you're thinking, oh my god, this would probably be tough to do, you are not wrong, because of this radical part. This actually might be very difficult to do depending on the curve. But in some cases it may be hard to do, but lucky for us it is a single integral and it's a definite integral. So if I have to ask you to do a problem using this formula, it is something that's extremely difficult to integrate. In the problem, I will specify that you can use, once you set the integral, you can use your calculator to evaluate it. But if I didn't say that, that would usually mean that you should be able to integrate and get an answer, and so you should try to do that. So therefore now I can formally define it. I'm going to go and put down definition. Okay. We'll let S, actually capital S, so make sure you make a note for yourself as a capital S. Let capital F be the lateral area, or lateral surface of a solid of revolutions formed it by rotating a curve alpha maybe I just say a curve x of t, y of t, where t go from a to, oh, actually, you know what, did I use a and b here? I did use a and b, so I'm going to have to adjust this. That would be b and that would be a. Now it's consistent. Okay, from a to b. So let S be the lateral surface of a solid revolution formed by rotating a curve around the x-axis. Okay, then the lateral area of S is given by the formula right here. So the formula is basically the formula that I boxed in right there, but now I have a lateral area function called sigma of S is equal to integral from a to b 2 pi y of t square root x prime of t square plus y prime of t square dt. So that would be the formula to find the lateral area of S, which is the lateral surface of a solid revolution. Now that we have this formula, we now can answer an extremely important question, and that would be, if you want to cover an entire donut with icing, how much icing do you need to use? Well, clearly, the amount of icing that you need to use would be based on the surface area of the donut, which is what we're going to try to calculate. So how do I actually form a donut? Well, this is how. Here's our example. We're going to let alpha be the curve in R2 given by the function g of t equal to a cosine t b plus a sine t, where t go from 0 to 2 pi, where actually I can exclude 2 pi. So what is this curve alpha? Well, actually, this curve alpha would actually be a circle because of the cosine t and sine t, and it has a radius of a. And then what does the b plus a sine t do? It actually form the center. So our center actually has 0b, and then we have a circle around b where the radius is a. And this is our curve alpha. Find the area of a solid of revolution by rotating alpha around the x-axis. And so what happened is, when I take this circle and rotate it around the x-axis, which is right here, that would form a donut. And with A being defined to be how big of the cross section of the donut is going to be, and B would define how big of a donut hole we have in the middle. And so with those two things, I can actually customize and make as big or as small a circle I can make. And of course, in this scenario right here, A has to be less than B, otherwise you have a connected donut without a donut hole. That would naturally not be a donut. So how do we actually calculate this surface area? Well, I guess we have no choice but to go for it. So in this case, I'm going to say that this area is equal to the integral from t sub 0 to t sub 1, or actually a to b, I'm sorry, that's what I use, so I'm going to say a to b, 2 pi y of t square root of x prime of t square plus y prime of t square dt. So let's see if we can actually figure everything here out. So I know y of t would actually be b plus a sine t. So that's good. A and b, well, a will be 0, b will be 2 pi. So that's good. We got those two things. Now I do need x prime of t and y prime of t, and then take the square root of them. So x prime of t would actually equal to negative a sine t. Y prime of t would actually equal to a cosine t. So therefore, square root of x prime of t, square plus y prime of t square, which is equal to square root of negative a sine t square plus a cosine t square. So that's just the square root of a square sine square t plus a square cosine square t. So therefore, that just come out to be square root of a square, which is just a. Well, technically speaking, absolute value of a. But here we assume that a has to be a positive number to begin with, because a here represents the radius. So I can safely just say a instead of absolute value of a. So now look like we have everything. So now I can plug them in. So my area would equal to integral from 0 to 2 pi b plus a sine t multiplied by a dt. Since a is a constant, I'm going to go and pull that out with the 2 pi. And I can actually integrate this. So that would be bt a sine t then goes negative a cosine t. Evaluate from 0 to 2 pi. So that's not too bad. So that equal to 2 pi a multiplied by b times 2 pi, which is 2 pi b, minus a cosine 2 pi. So that would be a cos a times 1, which is minus a. Minus, we're plugging 0, b times 0 is 0, minus a cosine 0, which is minus a. So therefore, negative a plus negative minus negative a become plus. So therefore, those two cancel out, and just leave you 2 pi b. So therefore, this seems to be my answer. So if you have a donut with a radius of the cross section to be a, and the rotation of the entire donut around the center of the donut hole is b, then the area of this donut will be 4 pi square a times b. Now we can actually now figure out how much icing we need to cover up a donut, which is important. So next time when you go to a donut shop and you want to question how much icing did they use, you can now throw this formula at them and make yourself look smart. Alright, that actually is the last thing I want to talk to you about in 8.2, and so that will be it. And next video would start on 8.3. Alright, I think that's it for this video, and I'll talk to you guys again soon. Okay, bye bye.